my previous videos, I talk about ideas such as the dot product, the norm, distance between vectors. These were all properties or operations or functions of vectors in 2 dimensions. But we can generalize these vectors to an n-dimensional space, often referred to as Rn. So if we were to say that A and B are in Rn, right? And maybe we'll say, let A and B be elements of Rn, where it's kind of n is a superscript there. This means that A is equal to some A1, I'm using an ellipses here, to AN, and that B is equal to some B1 through Bn. So just saying that there are n components of A, and there are n components of B. So A by itself is referring to the entire vector, whereas A with a subscript, for example, A2 will be the second element of the vector A. And we're purposefully using n here to keep it like an arbitrary number. So we recall, right, in R2, right, A dot B, right, the dot product, right, this is equal to the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between the two. But let's say we're in a 7-dimensional space. What does the angle between the 2 vectors mean? And so, because it's kind of hard to think about it, we've thought about the definition in a different way. So remember in a previous video, I showed that this formula for the dot product in 2 dimensions is actually equal to this formula, where we have A1, B1 plus A2, B2, right? These 2 expressions are equal to each other. So if we have A and B as elements of Rn, we can say that A dot B is equal to the sum of AI, BI as I goes from 1 to n. And to maybe write this out into more plain terms, this is A1, B1 plus dot 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 plus AN, BN. Now, interestingly, this is also equal to A transpose B. And this just goes from the definition of matrix multiplication. We can see that A and B are each n by 1 vectors, which makes A transpose, right? Not n, but a 1 by n matrix. So A transpose is just a row, right? 1 row, n columns. B, as we said, is an n by 1 matrix. And so, right, this will equal some matrix that is 1 by 1. And this will be the dot product. So by the definition of our dot product formula here in n dimensions, we have multiple ways of thinking about this and trying to solve for this quantity. Now recall in 2 dimensions that if we have a vector and we take the dot product of that vector by itself, right, using our geometric formula, we have this is equal to the magnitude of A times the magnitude of A times cosine of theta. But what is theta if it's the same vector, right? Theta is the angle between the 2 vectors. But if it's the same vector, then there is no angle, right? The angle measure is 0. So really, this is, so it's the magnitude of A squared, right, because we're multiplying that by itself, times cosine of 0. And now cosine of 0 is equal to 1. So this means this is simply equal to magnitude of a squared. Therefore, we can think about the length of a vector in Rn a similar way. So we can say that in Rn, the magnitude of A, or the norm of A, is defined to be the square root of the dot product of A and itself. And I use the word norm here instead of magnitude for multiple reasons. One, because, again, let's say we're in 7-dimensional space. What would the length of a vector necessarily look like? It might be hard to visualize this. And because norms are a special type of function with special properties. So this norm here actually is often referred to as the 2 norm or the L2 norm or the Euclidean norm. I'll just refer to it as the norm here in this series as it is the only type of norm I am referring to. But if you are interested, please feel free to look into different types of norms and how they work and what their shared properties are. Now finally, I want to think about the distance between two vectors, right? So let's recall that in R2, the distance between A and B, right, is equal to the magnitude of A minus B, right? We showed this in 2 dimensions. And so when we talk about distance between vectors, we will use this terminology here. So therefore, right, the distance between 2 vectors in Rn will be the norm of this, right? So it'll be equal to the dot product, or at least the square root of the dot product of A minus B and itself. And so now, right, we have a definition of distance that works for vectors in any n-dimensional space. So in summary, right, we had terms that we used specifically in 2 dimensions. These were terms that we could write out, we could draw on a chalkboard. But now we can use these when the number of dimensions is much more difficult to draw. Even in 3 dimensions, it's a lot more difficult to visualize these things. So taking certain properties that we found in 2 dimensions helps us use these ideas when we're in higher dimensional spaces.